Shielded Metal Arc Welding overview rant. I did one of these a while back, like 5-6 years ago, and I was looking at it and the quality was less than optimum. So I'm going to take another dive into it because that's just what the internet needs, is one more rant on somebody explaining how shielded metal arc welding works. So here goes. Oh, Gary A. Pace, PE, CWI, Katy, Texas. Our learning objectives for this adventure into the technical side of welding, we're going to talk about oxygen not being our friend, characteristics of electrodes. We're going to touch base on the American Welding Society classification system for carbon steel. We're going to talk about electrode characteristic groupings. We're going to talk fast freeze, fast fill, fill freeze, low hydrogen, and then we're going to wrap it up with SMAW electrode classification examples. I throw this in about half of my rants or my PowerPoint presentations, YouTube videos. Oxygen's not our friend. This is the main game for welding. We're trying to keep oxygen and nitrogen from crashing our party. So metals at high temperatures are reactive chemically with the main constituents of air, oxygen and nitrogen. Should the metal of the molten weld pool come in contact with air, porosity, oxides, and nitrides would be formed, upon which solidification of the molten pool could destroy the strength properties of the weld joint. Oxygen's not our friend. This is the main game of welding. So here's our shielded metal arc welding process. We've got a core wire, basically a piece of coat hanger, special magic coat hanger. That's the core wire. That's going to be the metal that gets deposited into our weld joint. We've got an electrode covering, which is a fluxing agent. We'll get into that later on. It burns, melts, it kicks off a shielding atmosphere. We get some molten slag. This helps protect our weld puddle from atmospheric contaminants such as oxygen and nitrogen. And this is the basis of this welding process. It's not super complicated. You get into the some of the applications with some of the really exotic materials that you could weld with this process, and you know, with preheats, post-weld heat treats and whatnot, there's some nuances there and it can get tricky. But the core idea behind this is you're running some electricity through a coat hanger, you're burning some wood chips and paper that are wrapped around it to kick the oxygen and nitrogen out of the zone near your weld puddle, and that's what we've got for shielded metal arc welding. So it gets back to, where does weld metal come from? Well, we're talking stick welding, shielded metal arc welding. Here's our electrodes, what they look like. It's just a piece of bare carbon steel wire. For the most part, if you're welding carbon steel, you could have stainless steel, but we'll just keep this to carbon steel. And it's covered with a flux that when everything breaks down, when you're running electricity through it, it's going to kick off a shielding gas, and it's going to kick off a flux or a slag that's going to cover the molten weld pool and allow your weld puddle to keep oxygen and nitrogen out of it. So the principles of SMAW. The gas-producing materials in the coating give out a lot of gas due to dissociation and combustion. The gases so produced form a protective gaseous shield around the arc. This atmosphere helps in shielding the arc of the weld metal from atmospheric oxygen, hydrogen, and nitrogen. Like I said, oxygen's not our friend. This is the basic principle of shielded metal arc welding. So what does all that mean? Well, basically it means we're going to have, when we're doing shielded metal arc welding, we're going to have an electrode holder and we're going to have an electrode. Our coat hanger covered with wood chips and paper if we're using 6010. And we're going to run electricity through this guy. That's our process. Our flux is going to burn and disassociate, kick off some gases that are going to protect our weld puddle. That's what we're looking for. This is our process. This is stick welded, shielding metal arc welding. If we were going to strike an arc, we're just going to weld. That's it. That's our welding process. Electricity is going to come down this cable. into our electrode holder. It's going to come out the end of our electrode. There's going to be enough heat there generated that it's going to cause everything to melt, and that's what our welding process is when we're talking about shielded metal arc welding. And as I mentioned before, there's a flux on here for 6010, E6010. It was one of the first electrodes invented. It's wood chips and paper basically on a coat hanger. Somebody back in the day figured out that they got better quality welds when you were burning a flux on the end of the electrode. I've seen old electrodes. A professor of mine had some that were had string wrap around them, and somebody had figured out that the string, when it burned, was going to give you what you needed. And then at some point, some company decided, hey, we can make our own without having guys wrap string around their electrode. But this is the basis of shielded metal arc welding. You basically got for steel, you've got an electrode, a piece of rod, a piece of coat hanger more or less, and it's covered with a flux. And the flux, there's various different types of fluxes that are utilized to give, different properties for different welding positions, metallurgical situations, chemistries, impact strengths, and whatnot. Characteristics of electrodes. So electrode covering is sometimes it's gonna add metal to the weld. It's going to create a protective gas shield around the arc and the molten metal. It creates a flux to clean the impurities from the molten metal. So depending on which type of filler material you're using, your flux could go in there and help clean the molten metal. It's going to create a hard slag covering to protect the molten weld bead as it cools. It's going to improve mechanical and chemical properties of the weld by adding alloying elements to the weld metal, depending on what you got going on. And it determines the current type and polarity specifications of the electrode. So here we have the American Welding Society classification system for carbon steel. So the first two letters are going to be the tensile strength. The next one is going to be the weld position. One is flat and horizontal, vertical and overhead. 2 is flat and horizontal only. And then 4 is flat, horizontal, vertical down, and overhead. Then you've got the types of coatings and the current. This is for carbon steel only. Manufacturers may use their own numbering system, but this is the AWS system, and pretty standard throughout North America. So when we're talking about tensile strength, this is what we're talking about. Here we've got the two horses trying to pull something apart. Just two opposing forces pulling something in a axial manner, I guess it would be. But this is tensile strength. So when we're talking about 60,000 pounds of tensile strength, we're talking about 60,000 pounds to pull 1 square inch of material apart. So that's what we're talking about when we talk about tensile strength. When we're talking about the welding positions, this is what we're talking about. 4G would be overhead position, 1G would be flat, 6G would be all position. 3G, you could either have 3G where you're traveling uphill or downhill. In this situation, we've got vertical up position where we're going to travel uphill, and there's more of these. This is just the main ones. I didn't get 5G or 2G in here. It would have cluttered it up, but these are our welding positions. Okay, so we talked about, our tensile strengths. E is for electrode. The first two letters are tensile strength. The next one is welding position. When we're talking welding position, we're talking, where the position that we're going to run the weld. So this would be the flat position, 1G, if I'm welding like this. If I'm welding, and I'm not going through all the positions, but I'm just giving you a general idea. If I'm welding uphill, this would be 3G. And then if I'm welding crossways like this, this would be 2G. If I'm welding overhead, it's 4G, and then there's a pipe position. But that's what we're talking about with this third number. This third number, we're talking about the welding position. How is the weld going to be positioned? Also, this is for carbon steel only. This is only for carbon steel. This one is tensile strength. How much is it going to take to pull that apart? So 60,000 pounds for every square inch of this weld material is what it's going to take to rip this apart. This last number is our flux. So this one is 6010, wood chips and paper. That's what it is. That's what we're talking about. Electrode characteristic groupings. Electrodes are also grouped according to their performance characteristics. So we would have like a fast freeze. A fast freeze would be something like a 6010. It would be a mild steel, quick solidification of the weld pool, deep penetrating. If you've ever welded with 610, it's got a really deep penetrating digging type arc. It's recommended for out of position welds. So if you need something where the weld puddle is going to run on you, you would do that. And you're not going to get high deposition rates with this, but it's going to freeze the puddle. It's a good rod. These are good rods, but they're for a specific use. I always use cutting tools as a example, with not everything's the same. So like a chainsaw and a scalpel, they're both cutting tools, but there's different uses, even though both are used for cutting things. Anyways, I digress. Fast fill would be like a 70-24 where you just absolutely need to dump some metal into a weld pool. Really high deposition rates, stable arcs, a really thick flux, and they're flat and horizontal positions only because the weld puddle is just so liquid. It takes it a while to cool, and you can't weld out of position with this stuff. It just doesn't work. Then you've got fill freeze, which is our general purpose electrodes. They're the characteristic of a fast freeze and a fast fill. So it's a little bit of both. And then low hydrogen kind of gets dumped in with the fill freezes because the pool will freeze on you, but not as quick as a fast freeze, but you also have the ability to deposit some weld metal into the weld joint at a reasonable rate that is a little higher than what you would get with like a fast freeze or a 60-10 type electrode. So here's a characteristic of some common electrodes. 60-10, cellulose sodium. You might have a little iron powder in there. It's an all position. It's got a digging arc. It freezes fast. It fills medium to slow. You're not really putting a lot of metal in there. It's a light, easy slag. It's a rough bead appearance. You can have really bad fit up and have a really poor fit up and if the welder knows what he's doing, he can, you can have some successful welds. So, and it gives you the amperage there for an 1/8 inch rod, 70 to 100 amps. Not a bad electrode, but it's got its place. Some people don't like to run it because there's a lot of fire involved, but actually it's one of my favorites. Our good friend cellulose, wood chips. These gases tend to produce a digging arc for deep penetration when you burn this stuff. This was one of the earliest type electrodes developed and is widely used for cross-country pipelines using downhill welding technique. It is normally used in the direct current with the electrode positive reverse polarity. So that's our good friend 60-10. Fast freeze electrode. Here's just a slide with that. Here's what your E6010 looks like. Low hydrogen potassium 7018. We're just talking with some iron powder is added to the electrode. And you're generally going to get some anything above 30 to 40%, and it's going to be E7018. But it just allows you to have a higher deposition rate than a filler material that doesn't have that iron powder chopped up and inserted into the flux coating. With our low hydrogen electrodes like E7018, we're going to have a little more iron powder than we would have in 60-10. This is going to give us a little higher deposition rate. All position, it's got a medium arc. The freeze is going to be a medium. The fill is going to be a little faster. It's got a little heavier slag than wood 6010 does, and it's a little more difficult to remove. The bead appearance is going to be completely different. It's going to be medium smooth with some spatter. Quality of fit up for successful welds. You got to have a good fit up with this. This stuff isn't as nearly as forgiving as 6010 is in regards to fit up. And your average amperage for an 1/8 inch rod, you're going to run it a little hotter than you're going to run 6010. You're going to run it at about 100 to 150 amps to really have some success with it. But the difference between this and 6010 is 6010, the flux is wood chip and paper. It's going to burn. This stuff, you're melting iron, and there's some other ingredients in that flux that are mineral based, and you're basically having to melt those. Whereas 6010, you're just burning it. This, you're melting it. So it's going to take some more energy to melt than it is to burn. So that's why, even though it's an 1/8 inch rod, you're still going to have to run it at a much higher amperage than you would a fast fill electrode like a 6010 that's got a cellulose covering. When we're talking about the groupings of electrodes, we're talking about what general categories do they fall into. So this would be like E7024, which would be a fast fill. All three of these electrodes have the same diameter. Our coat hanger, our electrode, our steel core is all the same diameter. But the difference is the flux. You can see that the flux coating on these three is completely different. My 6010, my 7018, and my 7024. 7024 is going to be the beefiest. It is a fast fill electrode. The idea behind 7024 is we're just throwing the coals to it. We're just trying to pump as much filler material into a weld joint to get a good deposition rate as possible. So there's iron powder in this guy. The whole idea behind this was just when they invented it, I guess they were trying to compete with wire feed welding to get deposition rates. So 7024. 7018's got some iron powder in there. It's a low hydrogen electrode. We classify that as a fill freeze or a low hydrogen. It does a little bit like the 7024 where we've got some fast deposition, but it also has the characteristics of our fast freeze, which is 6010. 6010 has a fast freeze characteristic. That weld puddle, if I'm welding out of position, it's going to freeze a lot quicker than something like a 7018, which is a fill freeze. And a 7024, there's no way in hell I can get it to run uphill, horizontal, or overhead because I've got a 2 in there, and the 2 says it's flat. I can either weld flat or horizontal fillets with this guy. So that's what we're talking about when we're talking about the characteristics and the groupings of shielded metal arc welding electrodes. When we talk about fast freeze, fast fill, fill freeze, and low hydrogen. It's just the general groupings. So 9018 would be a low hydrogen, and it would be a fill freeze. We're still going to be able to get some deposition with it, but not as much as if we use something like 7024. So that's what we're talking about when we're talking about characteristics. We're going to talk for a minute about specifications for filler materials. So this one is specification for low alloy steel electrodes for shielded metal arc welding. It's basically the recipe that tells the people on the manufacturing side of the universe the recipe that they need to use and the rules that they need to follow to manufacture electrodes. And then me on the receiving end of it, I can look at the same book and say, okay, you guys didn't meet your chemistry requirements, or you guys didn't meet your impact testing requirements if I have this stuff tested. But it's a universal standard by which filler material is supposed to be manufactured, and there's different ones. Some are for, you know, stainless steels and flux cord wires, and there's a whole bunch of them. And this is what the table of contents would look like, the scope, acceptance, certification. It just gives you the whole recipe of what needs to be done. What kind of tests, retests, chemical analysis, radiography, tension, just the whole batch of testing. It tells you what needs to be done to produce quality filler metal and then to be able to sell it. And then, but these are the universal rules by which the game is played for that type of filler metal being produced.
And the American Welding Society puts out a bunch of these books. Here's one for, what do we got here? For flux core electrodes. Figure out where my camera is. And then here's one for stainless steel electrodes for flux core. What's my last one? And then stick welding for, you know, there's a whole bunch of them. And the number is going to be listed up here. You know, so this one is AWS 5.4-92. And they, like I say, these are older editions. I don't have newer copies, but they come out with a newer copy every now and then. But these are the recipes that are going to tell you the chemistries. And if you're a manufacturer, it tells you, you know, how you're going to do all your testing and what's required and all that stuff. Another good place, well, I'm kind of on a rant. I got books stacked beside me. Another good place to acquire information in regards to filler materials is if you go and, you know, like this is the ESOP book, you know, Welding Filler Metal Data Book. I don't know, this thing's got a zillion pages. You pick something, you know, they're going to have it in there. They got all kinds of good information. And most manufacturers provide this. I think most of it's online at this point. This is kind of retro 1985, but a lot of times if you need to look something up, it's a good place to find it.
Here's another example where we've got E7024. You know, 70 is the tensile strength, 2 indicates the welding position, and 4 indicates, you know, it's an iron powder, titania, flux. And then we've got our good friend 6010. You know, 60 is a tensile strength, 1 is the welding position, which is all, and then 0 indicates that it's a cellulose flux. Here's one where we get a little off the rails. You can see that we've added the B1 and the H4R. Well, the B1 indicates, you're going to have to look that one up, but anytime you have like a letter and a number after the electrode designation, it's telling you that there's some chemistry, there's some added alloying elements to the filler material that are going to give it some special properties. Maybe an impact strength, maybe it's for weathering conditions, maybe it's for creep strength at a higher elevation. That's what that's telling us. And then if you look here, we've got the H4R. That's telling us the maximum amount of hydrogen that will be diffused from the rod. And then the R means that the rod is moisture resistant. That's what this is telling us. So there's a lot to this just beyond the regular, you know, E6010. Maybe you are running that. But if you, as you get into, you know, power plant situations or maybe nuclear or specialty situations, you're going to have these added designators onto the, you know, the tensile strength, the position, and the flux that are going to communicate more information to the end user about what this welding material is. And here's the, you know, the 4th digit in regards to the filler materials. You know, we can see that, you know, cellulose sodium is 1, and then, you know, iron powder low hydrogen is 8. If we got a 4 as the last one, it's iron powder titania. That would be like a 7024. Okay, we covered that oxygen's not our friend. That's pretty much one of the default settings of a lot of my videos. We talked about the characteristics of electrodes. We talked about the American Welding Society classification system. We talked about electrode characteristic groupings. We talked fast fill, fast freeze, fill freeze, low hydrogen. And then we touched base on a couple other items such as what is cellulose, and then, you know, low hydrogen potassium flux coatings. So not a bad rant for the most part, but that's what we covered.